Good afternoon, everybody. I'm Mudhakar Srivatsa. I'm from IBM. I'm going to be sharing the journey that we have had with PyTorch. This is a journey that started roughly about 2 years ago or so. We were working on distributed training, large-scale distributed training. The key challenge we had was we had to get this training running on commodity Ethernet. So that was the inception, and with that, we worked with the PyTorch team, introduced this rate limiter as a concept to make distributed training more efficient on commodity hardware. And from then, we have expanded the nature of work that we continue to do with PyTorch. In particular, make training more cloud native so that we can do checkpointing to cloud object stores, how to do hybrid sharding and checkpointing of hybrid sharded models again on various cloud object stores and so on. And these things further have evolved into how we invest and contribute to Torch Compile. So we have spent quite a bit of time in ensuring that fast inferencing is possible with Torch Compile, right? And that's the work that we have been doing since about October 2023. I'll give a little bit more examples of some of the work that we have done in the 1-minute deep dives on some of the topics. But continuing, this year our focus has been on Triton kernels. So we have developed a range of Triton kernels, especially for fusing dequantization and matmul, which is what you will need when you are operating on W4A16 kind of quantization, or fusing expert selection and MOE, expert selection and matmul for mixture of experts, right? That's another kind of work that we have done. Fast forward, we have also helped into how to do asynchronous checkpointing. This is a sort of a big feature in the sense that it reduces your checkpoint time by almost 10 to 20x. So this helps you do more frequent and periodic checkpointing, especially so that you do not lose precious GPU time and resources. Okay. So now I will spend a little bit of time into 3 specific topics that I want to go into, and it will all lead into what we are planning to do in the future with PyTorch. One of the key things that we did this year was work on speculative decoding. Many of you would have heard about it. It was introduced by Google in an academic paper over a year ago. Speculative decoding essentially speculates the next possible token, but it has a verification step built into it, meaning it will never produce a wrong answer because it has a verification step built into it. So it's a speculate but verify kind of a paradigm. And this paradigm can give significant boost to the overall inferencing times, inferencing latencies, throughput that you can get out of this. So what we have done is to build a range of speculators for the Llama models and the IBM Granite models. We have open sourced them via the Hugging Face ecosystem. We have also made the code available for inferencing of these models via Hugging Face TGI, text generation interface, and vLLM. Right. So the quick figure on the right-hand side kind of shows you the kind of speed up that you can get. 3 key factors. The more memory bandwidth constrained you are, the more is the X factor. The lesser the latency that you are expecting, more is the X factor. And more predictable your output is. Like for example, in a code like scenario, there are many tokens like semicolon and flower braces which are easy to speculate or predict. So you can get higher speed up for those kind of scenarios. The second key work that we have done is in terms of extensions and work with PyTorch FSDP. The starting point for us this year was FSDP with SDPA, scale dot product attention. And we have sort of worked together with Meta to evaluate 3 further techniques. First is selective activation checkpointing, which is a sort of a trade-off between compute and storage. More the activations I memorize, the lesser the recomputation required. So that's the selective activation checkpointing part. Hybrid sharding, which naturally leverages heterogeneity in your networking. So you could have faster local networks, slightly slower remote networking. And ultimately, Torch Compile, which is a method in which we can fuse multiple launchers so that we are doing fewer CPU to GPU round trip times essentially. Right? So all these factors collectively put together give us about 30% speed up. Now finally, going into the future, I want to talk about IBM Spyre. This is an AI accelerator that was announced at Hot Chips from IBM last month. This is a half-height, half-length 75-watt card which packs about 360 teraflops of compute within the 75-watt envelope. A predecessor of this, a single core of this, for example, runs in mainframes today. doing credit card fraud detection on credit card transactions. So this processes several billions of credit card transactions on a daily basis. And the core is embedded right next to the CPU. The key intent is that something like credit card fraud detection, we want a latency of under a millisecond. So that's the reason why we pack it so close. Now the key point I want to emphasize here is that this hardware is implemented as a PyTorch 2 compiled backend, so that native PyTorch programs can be compiled and run on this particular hardware. And we plan to expand on this with PyTorch FSDP compile and all of those training and inferencing running on this hardware in the future. That is our commitment to PyTorch, where we are taking PyTorch as our backend for our hardware for both inferencing and training into the future. With that, I'm done. Just wanted to say that yes, we are hiring, and if folks are interested, feel free to reach out. Thank you.